Hi everyone, welcome back to Medici Academia. So please don't forget to like our videos, share so that others too can be able to benefit from this tutorial. So we have did a lot of videos concerning mathematics, elementary mathematics, calculus at the same time, that of physics, general physics. So here we are talking about the physical chemistry. So please don't forget to like our videos, share so that others too can be able to benefit from that tutorial. So now today we're talking about physical chemistry. So there's a lot of things that we need to talk about here. Here we're talking about, let's say, properties of a gas. Properties of a gas and parameters that are related to that gas. But since we have discussed about that one when we are in primary school or secondary school to be precise, study about that. They talk us about, we have matters. Let's start from that. We have matter. Matter is anything that has mass and occupy the space, as you know. And we have three properties of matter. We have solid, we have liquid, at the same time we have gas. So the one we're talking about is for the gas. There's some properties of a gas like compressibility, reversibility, all those ones. So, and we also have parameters. So in case if you need materials, we are going to relate the material that talk about all those properties. What we want to base here is calculation involving that gas as well. So here we're talking about, we have two gas, we have regas, and we have ID gas. So most especially we're talking about ID gas. So when we have ID gas, it's a law, or it's just like a law, ID gas law. It's just like a law that obeys gas law, mostly like obeys Boyle's law, Charles law, and so on like that. But they have taught you all those ones, but still I will discuss about them, several examples involving Charles law, involving Boyle's law, and then we now move to ID gas law. So ID gas law is a law that obeys the general equation PV is equal to nRT. We are coming to that. So why the other one does not obey gas laws? It doesn't obey the Boyle's law, Charles law, and others. So let's first talk about the gas law that we have. We have some laws under the gas law. The first one we have what we call, let's first talk about Boyle's law. We have Boyle's laws. So for the Boyle's laws, that one is just like the one we have known in secondary school. So Boyle's law states that the volume of a fixed mass of a gas is inversely proportional to the pressure provided that the temperature are kept constant. But there are some things that we need to know in dealing with convections. Convection is very, very important. I will mention that the properties of that we have for a gas, we have pressure, we have volume. We have temperature, the most important one. So pressure as just like physics, we have what we call unit. Unit is what we use to recognize a given quantities. So there's a situation they will not tell you is actual thing they are talking about. They will just mention the unit. So if they mention the unit, you'll be able to know what you are trying to say. So when we have a pressure has some unit. It can be ATM. Is not ATM we are using to collect money. No, ATM in here is atmospheric pressure. It can be mmHg. This is a millimeter mercury. It can be Pascal. It can be Torr. Things are okay, and at the same time it can be Newton per meter square. These are the common units for the pressure. Please, you have to go through this very well. You have to master them. It depends on the approach of the problem. Either we have it as ATM, that's atmospheric pressure, or we have it as millimeter mercury, or Pascal, Torr, or Newton per meter square. It depends on the approach of the problem we are solving. If they use any of these, you know that they're talking about pressure. So for the volume, but don't worry, if you subscribe or just try to like our videos, try to subscribe so that you can have an access to download the material we are using. So for the volume can be cm cube, dm cube, meter cube, liter. So are the common one for the volume. So whenever you see this for the volume, either we have centimeter cube or dm cube or meter cube or liter is for the volume. Then for the temperature, the most common one in this case, temperature has like 4 units: Rankine, Fahrenheit, Celsius, and Kelvin. So the important one here is either degree Celsius or Kelvin. So even we talk about the conversion of temperature under the general physical time, we still talk about it here. We can convert a temperature from degree Celsius to Kelvin or from Kelvin to degree Celsius. If you want to do that, we use this formula. Temperature in Kelvin is equal to temperature in Celsius plus 273. We are coming to that. So let's talk about the law for the Boyle's laws. The law state that, just don't worry, I will state the law in the materials, but let me state it again. It's saying that the volume of a fixed mass of a gas is inversely proportional to the pressure, provided that the temperature are kept constant. Meaning, if the volume is increasing, the pressure will be decreasing. Or if the pressure is increasing, then the volume will be decreasing. So we can say mathematically volume is inversely proportional to the pressure. Can you see that? Or we can say P is inversely proportional to the volume. Anyhow, either you said A to B, or we said this is still giving the same expression. So now this is sign of proportionality. I can write this one as V is equal to K1 over P. Oh, you know, K is just constant. This can be written as V is equal to K over P. So if I cross multiply, that means that we have PV is equal to K. So in general, you can have P1 V1 is equal to P2 V2. So this is the formula for what? This is the formula for Boyle's law. Can you see that? So the P1 here means the first pressure, the initial pressure. The V1 means the first volume as well. The P2, the final pressure, and the V2 also means what? Also means the final volume. Let's see like one example or two examples in this case, then we move further. So in general, for the Boyle's laws, we apply the formula P1 V1 is equal to P2 then V2. So this is general formula for the Boyle's laws. So now, let's see the example. Question 1, maybe they said a volume 20 cm3 of a fixed mass of a gas. Mass of a gas. It's at a pressure of, let's say, 10 millimeter mercury. Find the new volume if the pressure becomes 20 millimeter mercury. So just like as I used to say, you know, what's important in physics or chemistry is the data given. The first thing, when you are given a problem, bring out the data. After bringing out the data, then you'll be able to know how we are going to fetch out the particular parameters. So now, for example, let's see this question. A volume of a volume 20 cm3. That's our V1. Our V1 we have here is a 20 cm3 of a fixed mass of a gas at a pressure of 10 millimeter mercury. P1 is a 10 millimeter mercury. Find the new volume, that is, we are looking for the V2 if the pressure become 20. So if our P2 become 20 millimeter mercury. Can you see that? So now we can go give out the what do you call it? Our formula is a P1 V1 is equal to P2 V2. So my P1 we have here is 10. I have 10 multiply our V1 we have is 20 is equal to our P2 that we have there is 20, and our V2 is V2, what we are looking for. So now I'm looking for V2, divide 2 by 20, divide 2 by 20, this cancel this, and we have V2 is, we can see 20 can cancel 20 here. What do we have now? We have 10 cm3. You can see it's very straightforward. So you may be asked to find anything. It may be either P1, you may be asked to find either P2 or V2. So let's see another question. I want to bring another question in form of another way. Let's maybe they said a volume V1, let's write that one, of a fixed mass of a gas at a pressure of P1 as well. Find the new volume if the pressure is half of the original pressure. Half of the original. Let's put it that way. If volume V1, so that's our V1 is still V1, of a fixed mass of a gas at a pressure of P1, our P1 is still P1, our V1, just like our V1 is V1 and our P1 is P1. So now say find the new volume, meaning we are looking for the V2 if the pressure is half of the original. That is, if the P2 is half, what is the original? The original is P1. If it's half of the original one, which is a P1. Can you see that? So now our formula that we have is a P1 V1 is equal to P2 V2. So my P1 is P1, my V1 is V1. So my P2, what is my P2? My P2 is half of P1. Can you see that? So V2 is still on what I'm looking for. You know, you can see if I cross multiply here, you know, the 2 that we have here, we multiply this. That means here we have 2P1 V1 is equal to P1 V2. So since we are looking for V2, divide by P1, divide by P1, this cancel this, and we have V2 is equal to P1, cancel P1, then we have 2 V1. So that means our V2 is equal to 2 V1. Can you see that? So that's all about what we have for the Boyle's law. So the other one we are going to talk about is Charles' law. We have another one, we call it Charles' law. We have Charles' law too as well. We have Charles' law. So this law is also just like a law. It's saying that the volume of a fixed mass of a gas is directly proportional to the temperature, provided that the pressure are kept constant. You know, that other one is inversely. But under the Charles is directly proportional. Meaning, mathematically, we can say volume is directly proportional to temperature. So now, this is a sign of proportionality. I can have this one to be V is equal to KT. If I make my K as the subject, divide 2 by T, this cancel this, and we have K is equal to V over T. So in general, that is a V1 over T1 is equal to V2 over T2. So this is for the Charles law. Can you see the difference? You know, the other one is P1, V1. So but here, what we have is a P2, a V1. So now, what is important here is the conversion of temperature. You know, I told you earlier, the temperature can be either degrees Celsius or it can be Kelvin. So the one you are given will depends, are you going to convert the values or you leave the value as the way it is? If you are given, in mostly problem, if you are given the value in degrees Celsius, you have to convert it to Kelvin. Or if you are given the value in Kelvin, then you don't need to convert. I hope you are getting what I'm saying, right? Let's see a question and understand what I'm saying. So in general, I can write that the Charles law is V1 over T1 is equal to V2 over T2. So this is for the Charles law. So let's see an example like this. Maybe they said a volume of a fixed mass of a gas, a fixed mass of a gas, a volume, or let's say a volume 10 dm cube of a fixed mass of a gas, let's say at 27 degrees Celsius. Calculate the new volume if the temperature becomes, let's say minus 73 degrees Celsius. So now let's see this one. They say the volume 10 dmq. The first thing I do tell you, you have to firstly put out the data. So our V1 we have here is at 10 dmq of a fixed mass of a gas at 27 degrees Celsius. That's our T1, 27. Do we need to convert this one? Why? Why do we need to convert it? Yeah, because the value that we have there is in Celsius, so we have to convert it. Remember the formula that we have, T in Kelvin is equal to T in Celsius plus 273. So T in Kelvin here is going to be, T in Celsius we have it to be 27, then plus 273. So here we are going to have this one to be 300 Kelvin. Can you see that? Yeah, fine. So now we have converted this one to Kelvin now. So let's go further and find the value of the other one. So now what we have done is this. So the next is to put the values of, calculate the mean volume. We have to find the V2. If the temperature become minus 73, so that is our T2 is minus 73 degrees. So this one too, we have to convert it, right? So now the same method, T in Kelvin is equal to T in Celsius plus 273. Then T in Kelvin is going to be minus 73 plus 273. So here we are going to have 100 Kelvin. We are going to have 200 Kelvin. Can you see that? So that means my T2 is not going to be, and my T1 is not going to be 27. What are we going to do for T1 now? Yeah, we are going to use 300. So that means our T1 is 300 Kelvin, and our T2 that we have now, we have it to be 200 Kelvin. So what we are looking for is the V2. I hope you are following, right? So now, since we have gotten out all the data needed, we have gotten T1, we have gotten T2, we have our V1. The only thing we are looking for is our V2. So let's apply the formulas. So back to the formula that we mentioned, we said the formula is V1 over T1 is equal to V2 over T2. So from here, our V1 is 10. Can you see that? We have it to be 10 divided by our T1 that we have here is 300. We have it to be 300 is equal to V2 is what we are looking for. Please, we need calculator. So V2 then, and our T2 that we have from here, our T2 is, we have it to be 200. So now, the next is to make our V2 are the subject of the formula. If I cross multiply, we have 300 V2. That is, how did I do that? Let me show you. The 300 we multiply the V2, the 200 we multiply 10. That means that we have 300 times V2, this times this, is equal to 10 multiplied by 200. Can you see that? The only thing we are trying to do is we try to cross multiply it. So I don't want to clean this one, so that we'll be using this unit. So now 300 times V2, of course, you are going to have 300 V2 is equal to 10 times 200, we are going to have 2,000. So now what I'm looking for is V2, right? So divide by 300, divide by 300. So that means that we have V2 to be. So this can cancel this cancel this. 20 divided by 3, 3 in 20, that's going to be 6 point, so let's do this one as a calculator, right? So 3 in 20, it's going to go in 18. That's remainder 2. Then 3 in 20, that's going to be 60, 60, 60, 60, let's say 67, depending on the approximation. Then D and Q. So that's what we have for the temperature for the Chancellor as well. So it depends on the one you have to calculate, and that one too can come in form of what problem. Just make sure how you are going to make use of the formula. It can never be changed. It's always V1 over T1 equal to V2 all over T2. So the law that now obey this Boyle's law and Charles law, we call it ideal gas. We call it what? We call it ideal gas. So ideal gas. Let's go to ideal gas sharp. Then we can round it up. So for the ideal gas, let me just give you general. You see the definition in our materials. So to save our time, for ideal gas, the formula is given as this: ideal gas. We use the formula PV. That's a derivation. So please, in case if you need that one, you check our materials. So you see the derivation of it every steps. So that's why we are trying to break it down. So in these parameters, let me just try. You can see just like a combination of both Charles law and Boyle's law, isn't it? You know, we have another one. We have, okay, there is one that we have, we call it general gas law. I hope you remember that one. Okay, general gas law. Maybe I should just quickly derive that one. We have what we call general gas law. It's the law that combines both Boyle's law and Charles law together. You know, this is for the Boyle's law. We have P1 V1 equal to P2 V2. This is for the boys. Then we have V1 over T1 is equal to V2 over T2. This is for the Charles, right? So the law that combine them together, we call it a general. Let's multiply this side together, and this side, you know, we cannot have a repetition of V1. As we're going to have P1 V1 over T1 is equal to P2 V2 over T2. So this one we call it a general gas law. So you can see the P1 is the first pressure, the V1 is the first volume, the T1 is the first temperature, the P2 second pressure, the V2 second volume, and T2 is a second temperature as well. So the law that will be this, we call it a ideal gas law. So that's why we have it to be PV is equal to nRT. So here, the P that we put here, the P here, it means pressure. P here means pressure. Then the V here that we use here, it means volume. N that we use there, it's called number of mole. So I will also talk about how to calculate number of mole in chemistry. You know, that one is also important. The R, we call R as molar gas constant. Molar gas constant. The value of that one is constant. It can be 8.314 something. Then in some cases they can use 0. It depends on the one you asked to use though. So please take note of that. Then T that we put there, T is a temperature. So what I was trying to say in essence is that in some problem, you may be asked to find anything in which the number of mole is not given. So if the number of mole is not given, we have, you know, in general, we will call in secondary school the totals are mole, right? So can you remind us the formula for mole? Do you remember the formula for mole? Yeah, so we know that mole is equal to mass, reactant mass. Let me put it that way. So we know that mole is equal to reactant mass. We know that mole is equal to reactant mass over what? Over molar mass. So this formula needs to be applicable when, so this formula can be applicable when the mole is not given directly from the questions. So if the mole is not given directly from the questions, we make use of this formula to find the mole first. And after finding the value of the mole, then we can substitute it back to that equation. So I will solve like 3 examples here. And you can see this one to also have a way of calculating the molar mass. I hope you remember that one, right? Let's solve like 2 examples, then we move further. We move to the one that serve as our business here. So let's, for example, let's say I'm coming back to this. I'm coming back to ID gap. It says PV is equal to nRT. So let's use these questions. Maybe they said how many mole are there in 20 grams of calcium triisobicarbonate 4, given that calcium is 40, carbon is 12, and oxygen is 16. So here, look at the question. It said how many mole are there in 20 grams of calcium triisobicarbonate 4? So meaning I have to find the first thing I will give. I have to find there. In the problem, we are given the mole. We are given the mass. Can you see? But do we have the molar mass? No, there's no molar mass. Since there is no molar mass, I need to first calculate the molar mass of calcium triisobicarbonate. What? Calcium triisobicarbonate 4. So from the formula, we know molar mass of calcium triisobicarbonate 4. How are we going to calculate that? So calcium is 40, carbon is 12, oxygen is 16 multiplied by 3. So here I can have this one to be 40 plus 12 plus 16 times 3, we are going to have 48, right? So if that one is 48, then here, if I add this one together, we are going to have 100. So now I can go to the formula for mole now. So number of mole is equal to reactant mass, this mass, over molar mass. So here I can have mole to be equal to, so the mass that we have from the problem is 20 grams divided by the molar mass that we have is 100. So now this cancel this. So 2 divided by 10, I think that was going to be 0.2, right? 0.2. So that's our mole. So you can see, so in some questions under this ideal gas, you will need to calculate your mole before you substitute back to this equation. So let's see like examples. Okay, let's look at this one before I move further. In this material that we have here, the question says that, let's look at some examples here. Yeah, the question says, calculate the number of mole of the following gases. 1A, 5.6 gram of nitrogen gas. So B, 1.32 gram of carbon dioxide, and we are given that nitrogen is 14, carbon is 12, and oxygen is 16. So this is just like a 2 problem. We have to find their moles. So meaning I'll find the mole of the first one, at the same time I'll find the mole of the second one. So for the first question, question A, there we are given mass, right? We are given reactant mass. That reactant mass, the mass that we have there is 5.6 gram. Then at the same time, you can see it's nitrogen gas. So since nitrogen gas, there I can say this is going to be, nitrogen is 14. That's going to be 14 multiplied by 2. So 14 times 2, that's going to be 20. I hope you are getting it right. Yeah, fine. So now the formula, I have the formula, which is a mole is equal to reactant mass over molar mass. So now I can have mole equal to, so reactant mass that we have is 5.6 divided by the molar mass that we have now is 28. So let's define this with our calculator and see what's going to be the result. Doctor, please, is it working? And the mic too. Mic. So we do that. What we have is 0.2 mole. So we have our mole to be. So I will leave the second one as exercises, simple exercises, but let me just give you the clue. We have been given the mass, isn't it? Yeah. So now, do we have the molar mass? That's going to be our first priority, is to firstly find our molar mass. How can we find the molar mass of carbon dioxide? Molar mass of CO2, carbon is 12, oxygen is 16, then multiply by 2. So here we have 12, 16 times 2, that's going to be 32. Then 12 plus this, we are going to have 44. Then you can just mass of molar. I even give you the answer already. So now that's all about for this. So what we are trying to say in essence is that there are some problems that we need to find all this before we can be able to find to apply the formula. So let's see some examples then. Let's see some examples. Let's see some examples then. How can we make use of ideal gas? Let's see this problem. They said, what pressure and ATM, atmospheric pressure, is exacted by, let's see, 10 grams of hydrogen triazonitrate 5 in a liter, flask at 293 Kelvin. So given that hydrogen is 1, nitrogen is 14, oxygen is 16. So this is what we have. And here we are asked to use molar gas constant here to be 0.0821 liter ATM per mole per Kelvin. So the unit. So that's what we are asked to use here. So let's see how we are going to approach this problem. As I told you earlier, we are going to use the same method. Now, what pressure? Meaning, I'm looking for the pressure, right? We are looking for the pressure in ATM, meaning that the value of the value we are going to get it should be in atmospheric pressure. Is exacted by 10 grams of this, so we are given mass. We are given mass to be 10 grams of HNO3. So now from there we can even find the molar mass. Molar mass of HNO3. Molar mass of HNO3. So that's going to be, hydrogen is 1. That's 1. Nitrogen is 14. Then oxygen is 16 multiplied by 3. So you can see hydrogen is 1. So nitrogen is 14. And oxygen that we have is 16. Then we have 3 here times 3. So here we are going to have 1 plus 14 plus 16 times 3. Definitely you are going to have 48. The 1 plus 14 we have 15. Then 15 plus 48, we are going to have 63. So now we have known our mass. We have gotten our molar mass. We can quickly find our what? Our mole. So now we have the formula that mole is equal to reactant mass over molar mass. So now I can have mole to be equal to, so reactant mass that we have from here is 10 divided by the molar mass that we have now is at 63. So 10 divided by 63. So that one gives us 0.159 by approximation. 0.159 by approximation. So now, in a liter, what does that mean? I told you earlier, the volume can either be cm cube, dm cube, meter cube, liter. So the liter is for the volume, and the value of this one is even given in volume. To convert that one in a liter. So meaning our volume is 1. So 1 liter at 293 Kelvin. You can see that one too is in Kelvin. So we are given temperature. We are given T to be 293 Kelvin. So recall I told you if the value you have is in diffusion, what do you need to do? You need to convert it. But now, let's apply the formula. Since we have all the data, so the formula is a PV is equal to nRT, right? So now the P is what I'm looking for. So I have to make my P at the subject, divide 2 by V, divide 2 by V. If this cancels this, we have P to be equal to nRT all over V. So here I can have P to be, so our N, what's our N there? Let's check our N. What do we have for N? Our N is 0.159 multiplied by our R. We are given R to be 0.0821. I told you it depends on the data you are using for your R. We have our R to be 0.0821. The temperature that we have, what's the temperature? Temperature is 293, then divided by 1. So we just multiply all this together. Whatever you get, that's going to be your result. So that's all about for that one. And in some situations, it may require density. Let me prove that one too for you, so that you'll be able to have a better knowledge on that one. Because in some problem, they can relate it to density. So you'll be wondering, how can we have this one in form of density? You see the beauty of chemistry now. So let me derive the formula for you. You can see some problem that will require for you to use density. So how come that you can have a density here? Please don't forget this. And if you check our material, we even give you a clue on how we can convert all this, maybe from ATM to millimeter mercury, or from millimeter mercury to Pascal. So this one, you see it in our material, inshallah. Just try to subscribe to our channel so that you can enjoy us more. Now, from this formula, look at it. We have PV is equal to nRT. You'll be wondering, how come that can we have a density here? Of course, we can have a density. Let's see the proving together. Normally we know that density, do you remember the formula for density? What's the formula for density? Density is a mass over volume, right? Can I just use a symbol for, let me use D for density, mass to be M over V. So now, and we know, according to what we put now, we say that number of moles is equal to mass over molar mass. Remember these two also? Now let's substitute the two to use formula. So I can have P, V now. You know, from here I can make my V at the subject. If I make the V at the subject, that is a dV. Don't forget the D here we are talking about here is density. The V we are talking about here is volume. So it's equal to M, then divided by D, divided by D. So that means V is equal to mass over density. So now, if I, instead of using volume now, I can put this there. That is a M over D is equal to number of mole that we have is mass over molar mass. Then we have RT. Can you see that? So if I cross multiply, I will have PM multiplied by molar mass is equal to M RT D. Can you see that? So mass can cancel mass now. So that means that we have P multiplied by molar mass is equal to RT D. Can you see that? We have already formulated the formula into another thing entirely. You can see that. So the P is still pressure, the mm is the molar mass, R is the molar gas constant, T is the temperature, and D is the density. So if you are given a problem related to this, you can, let's see one examples, then we'll move further. So let's see this one. Let's see this example. Let me write down the formula here. P times molar mass is equal to RTD. So let's see these examples. Gombe, can you time? What is time? Nitric acid. Okay. Nitric acid. Nitric acid is a very important industrial chemicals. Industrial chemicals is made by dissolving the gas, NO2 in water. Calculate the density. Calculate the density of NO2 at 1.24 atm and 50 degrees Celsius. So given that N is 14, oxygen is 16, and the R they want us to use it, they said we should use R to be 8.314. Yeah, so let's see how you are going to approach this one too as well. They said nitric acid is a very important industrial chemical. It's made up by dissolving the gas NO2 in water. Calculate the density of NO2 at 1.24 atm and 50 degrees Celsius. Then we are given all those parameters. So now recall, look at the formula. So the only thing I need to find is to find the molar mass, right? Yeah, fine. So let's find the molar mass of the gas we are given. Molar mass of NO2. So from here, you are given N to be 14. That is 14. So oxygen is 16, as we are given there, 16 times 2. So here I can have 14 plus 16 times 2, we are going to have 32. So 14 plus 32, what are we going to have? Of course, we are going to have 46. So now, from the data, we are given pressure to be 1.24 atm. And at the same time, we are given temperature The that we have is 50 degrees Celsius. So now, since we are given this one in Celsius, I can convert that one to what? I can convert it to Kelvin, right? So that is going to be temperature in Kelvin is equal to temperature in Celsius plus. I hope you remember this formula. You know, I told you it can convert from temperature. You can convert from where? From Celsius to Kelvin. So now the value we have is in Celsius. So of course we have to convert it to Kelvin. So here I can have temperature in Kelvin here to be Celsius that we have is 50 plus 273. So 273 plus 50. I think here we are going to have 323. 323 Kelvin. 323 Kelvin as well. So now, so after getting that, then we can just substitute back to the formulas. So the formula we have, the derived is a pressure times molar mass is equal to molar gas constant temperature density. So since we have to find the density, I can make the density as the subject, divide both sides by RT, divide both sides by RT. So if this cancels this, I can have density to be. So our pressure, we are given pressure to be 1.24. It's 1.24 times the molar mass that we have. We get molar mass to be 46. That's going to be 46 multiplied by divided by molar gas constant we have to use 8.314. The temperature that we have is at 323. So now let's see the result of this. This is at 1.24 multiplied by 46. Or let me just press it once and for all, right? 1.24 times 46 divided by 8.314 times 323. So here, if I do that, what we have is a 0.02. So density, you can see, for mass over volume, you can see gram per, what is the volume that we have here? Anything, you can depend on the unit, you can say gram per liter, so gram per the conversion, dm or meter cube. So that's all about that one. So another one we have is we have what we call Dalton's law of partial pressure. Dalton's law of partial pressure. So that one too it's so simple. So when we be asked, maybe you have more than two pressure, but don't worry, in our materials we are going to state all those laws and the material needed and the data needed for that. But in short, let me just solve some problem there. Just related to this, when we are given two gas and we have to find it maybe either pressure or volume or whatsoever. Let's see examples of that, then you'll be able to get the concept. Like this one, they said, what pressure, Dalton's law, we're still under that ID gas, Dalton's law of partial pressure. Let me include that one too. Partial pressure and ID gas pressure. Now, they said, what pressure is exerted by a mixture of 2.00 gram of hydrogen gas and 8.00 gram of nitrogen gas at 273 Kelvin in 10 liter vessel. In 10 liter vessel, given that hydrogen is 1 and nitrogen is 14. So this is another problem. And here we are asked to take our R to still be 0.0821. So now you see, this one is just like two questions in a single one, right? So what do we need to do? Just calculate the one after the other, then we find the total pressure. So now, what pressure? We have to find the pressure. It's exerted by a mixture of, it's two gases now, hydrogen gas and nitrogen gas. So we can do it in two ways, but the simplest way, first we find the pressure of the first gas, calculate the pressure of the second gas, then you just add them together. So for the first gas, mass of hydrogen gas, we are given the value to be 2.00 gram. You know, from here, I can find my molar, I can find the number of moles, right? You know, even for the molar mass of hydrogen gas, that's going to be 1 times 2, and that one is 2. Then we know number of mole is equal to mass over molar mass. So our mass that we have is 2 gram. Then we also have 2 as the molar mass. That's going to be 1.00 mole, right? That's for the what do they call it, for the hydrogen gas. So then, and 8.00 gram of nitrogen gas. Let's calculate. That's mass of nitrogen gas as well. We are given the value to be 8. So let's quickly calculate that one too. Number of mole is equal to mass over molar mass. But you know, I can find the molar mass of this one. That's going to be 14 times 2. You know, nitrogen is 14 as we are given here. So 14 times 2, that's going to be 28. So here we are going to have 8 divided by 28. So let me see the result of this. 8 divided by 28, I think what we have is a 0.29 by approximation, 0.29 mole. At 273 Kelvin, that's our temperature. Okay, temperature we have is 273 Kelvin. Then in 10 liter, the volume is 10 liters. So, and we are given R to be 0.0821. So I'll find the pressure in the first one. I'll calculate the pressure in the second one, then I'll down add them together. So let's calculate the one after the other. Pressure in the first one for the hydrogen gas, that's PV equal to nRT, right? So now if I make my P at the subject, divide by V by V. So if this cancels this, we have pressure across the hydrogen gas is equal to number of mole that we have for that one is what is itself? We have it to be 1. Our molar gas constant, we have it to be what's our molar gas constant? Molar gas constant is 0.0821. The temperature that we have, what is our temperature? Temperature is 273 divided by the volume that we have is 10. So now I can have pressure of hydrogen gas is equal to 0.0821 multiplied by 273, then divided by 10. So if I do that, what I have here is at 2.24 atm. That's for the first one. Then for the second gas, it is a nitrogen gas. The same method is a PV is equal to nRT. So then make P at the subject, divide through by V, divide through by V. If this cancels this, we have P is equal to nRT over V. So that means here we have pressure of nitrogen gas as well. So number of mole of that one, we have it to be 0.29 multiplied by molar gas constant, we have it to be 0.0821. The temperature that we have, what's our temperature? Is at 273 divided by the volume is 10. So now here I can have this to be 0.29 multiplied by 0.0821 multiplied by 273, then divided by 10. So what I have here is a 0.64. By approximation, we can say 0.65 atm. Right? So we have calculated the two. This is for the what did you call it? This is for the pressure across the hydrogen gas. This is across the nitrogen gas. So we have to find the pressure. So I can now say total pressure now is equal to pressure across the hydrogen gas plus pressure across the nitrogen gas. So the one across the hydrogen gas, we have it to be 2.24. That's 2.24. The one across the other one is 0.65. Just add them together. Whatever you have, okay, let me add them. 0.65 plus 2.24. So if I do that, what I have here is at 2.89 atm. You can see, just so simple. So even if it's the gas, we find for the first gas, for the second gas, third gas, then add them together. Even we have another one, we call it a mole fraction. Let's talk about that one, then we'll round it up. We also have what we call mole fractions. When we are given the value in terms of mole fractions. So in that, what you need to do is, you just calculate the total number of mole fractions. It can relate to that one too, mole fractions. You know that in that one is that if I have like 3 gases, let's say I have like 2 gases or 4 gases, let's say we have gas A, B, and C. So what I will do is I will only find their number of mole. Number of mole in total is going to be Na plus Nb plus Nc. Get that? So after that, if I want to find the pressure across each of them, then we have pressure across A is going to be Na over the N total multiplied by the P total. You will be given P total from the problem. For the B also, it's going to be Pb is equal to Nb over N total multiplied by P total. And like that for the C also. Let me solve one question from there. Is it working? No. Let's solve one question from there, then you see how we are going to make use of that. Okay, let's look at this. Let's look at this problem. They said the total pressure exerted by a mixture of 2 gases, A and B, is 76.5 millimeter mercury. The number of mole of the 2 gases are 0.0075 and 0.0040 respectively. Calculate the partial pressure of the 2 gases. Calculate the partial pressure of the 2 gases. You can see this problem. Just so simple and straightforward. There's nothing to worry about this. It's just so simple. Now let's see how we are going to approach that. They said the total pressure exerted by mixture of 2 gases, A and B. You know, that the gas they're talking about is A and B here. So the total pressure exerted between that one is at 76.5 millimeter mercury. The number of mole of the 2 gases are this and this. That is, the number of mole of A is 0.0075. Then for the B, we have it to be 0.0040. The answer calculate the partial pressure of the 2 gases. So we should find the pressure across A and total pressure across the B as well. So what's the first thing I told you to do? You first find your N total effect. So N total is going to be Na plus Nb. So now our Na from the problem, we have it to be 0.0075 plus Nb is 0.0040. So 0.00075 is 0.0040. So if you add that one together, we're going to have 0.0115. 0.0115. So that's our total mole. So if I want to find, I will find one that you find the other one. If I want to find for the first gas now, that's going to be Pa. Total pressure across the first one is equal to Na over N total multiplied by P total. Can you see that? So I will leave this one as an assignment, the second one. Okay, how can we find for B if I want to find B now? How can we find that? Yeah, it's going to be Pb. Yes. Exactly. Over P total. You can see that it's very simple. So now from here, what do we have for Na? Our Na we have is 0.0075. Our N total we have is what's our N total? N total we have is 0.0115. P total, what's our P total? P total that we have is 76.5. So let me multiply that one together. So we have 0.0075 multiplied by 76.5 divided by 0.015. So what we have is 49.89 millimeter mercury. So that's for the first one. Then you can go for the second one too as well. Just find the same method. You go here, just find your, we have been given the NB already over N total multiplied by P total. So that's all we have for these chapters. So please, we talk about the gas law, how to make use of Boyle's law, Chance law, at the same time, general gas laws, which is we mentioned ID gas, how to read the formula as well. We'll talk about that one too as well. Then at the same time, we talk about that law of partial pressures, how we can use that one to relate it to the ID gas. So that's all we have for this chapter. So we are going to have more exercises. So in case if you miss any video, just kindly subscribe, like our videos, share the videos so that other two, we are not the best, we're just trying our best to be the best. So please don't forget to like our videos and share. Thanks for watching.